quantum computing and quantum sensing, bridging theory and real-world application. Please go ahead, Dr. Amaria.
Thank you very much, Dr. Zidan, for the invitation and for having me. So just want to make sure that you can see the screen or not yet.
We see your camera, but presentation is not shared.
Oh, okay.
Okay, it's good now. Please full screen.
Yes. All good?
It's good.
Yes.
Please go ahead.
Yeah. Thank you so much. Once again, Dr. Zidan. It was nice meeting you at MENA Quantum last year, and good to have this talk on the International Year of Quantum Science and Technology. As we all know, that this 2025, this year by UNESCO, it is we are celebrating it as Quantum Year, 100 years of the quantum science. So I think it's good to talk about quantum. We are expecting a lot of activities around the world highlighting the quantum technology or quantum physics in general. So today, as Dr. Hassan mentioned, I am a postdoctoral associate at the Center for Quantum and Topological Systems from New York University, Abuظbي. And my title is Quantum Computing and Quantum Sensing, Bridging Theory and the Real World Application. So I will go through with the kind of intro of quantum computing, and then we'll move to the quantum sensing thing. Okay, so let's go. Before going to the topic, I'll just share my general information regarding myself. I'm born and raised in Pakistan, and my high school and all education until master's is from Pakistan. I have my master's degree from Quaid-e-Azam University, Islamabad. Maybe you can see the mouse, right? Yes. So after master, I moved to United Arab Emirates University for my PhD. I did my PhD with Professor Osama Al-Khwaja in nonlinear physics, designing optical devices using solitary waves or nonlinear waves. And then I I've worked before joining New York University. I was in Khalifa University for a postdoctoral project on nonlinear physics. So this is my LinkedIn. I would love to connect with anyone interested in these fields of quantum. So this is small intro for my center where I work. This is Sham Sati. He's our director of the Quantum Center. We call it Center for Quantum and Topological Systems. It is purely it was theoretical, and then we are adding the hardware part also in the center. So our center has 5 co-PIs, now more than 10 postdocs are working, and we offer many courses on the quantum, and we organize multiple conferences every year on quantum science. This is our research group. You can see the variety or how much diverse our group is, starting from Tim Bernes is from NYU Shanghai on quantum physics. Then we have quantum sensing, quantum algorithms. These are different research lines in our center. Quantum machine learning is there, and physics-inspired machine learning is also. And of course, the name itself says topology, so we are also working on topology on the quantum computation thing. Why to embrace quantum? If you see this map, how many countries and how much budget they have designated for the quantum technology. So you can see it's... Okay, so NYU Abu Dhabi also took this initiative of quantum through our center, and we want to accelerate the quantum research in the region, in UAE and MENA region specifically. So we are, I think it's the true time to embrace quantum and accept it and move with the quantum technology. This picture, if you can see, this is 1940. It's the first ever computer, classical computer, And these days, it's now the latest chip of the classical machine is like this much small, right? The size of the computers or the transistors, things getting smaller and smaller. But how small we can go, we have to break, like the more smaller you're moving, actually you are going or entering into the quantum regime. So what is actually quantum? Quantum is actually the study of behavior and the interaction of very small objects. How small? It could be like atoms and molecular level. So this slide will give you the idea that when I say really small, how small, what does it mean? So you can see that at this length scale, when we enter to 10⁻⁻⁶ or nanometers and angstroms or these things, when we are talking about this length scale, actually we are in all talking about quantum regime, where classical mechanics, Newtonian mechanics or Newtonian laws becomes invalid, right? So we have to enter, we have to embrace quantum, and without using quantum mechanics, we cannot solve these problems which lies in this regime, which is, we call it quantum regime, very small micro scale level, right? So with the quantum, quantum mechanics, we define quantum computer that performs those calculations, which is based on these quantum mechanics. So what is quantum mechanics? Which actually behavior of the particles at the subatomic level, right? Very small level. So any machine which is based on the laws of quantum mechanics would be declared as quantum computer. How powerful quantum computation would be, right? In the quantum systems, actually possibilities count even if they never happen. And each of exponentially many possibilities can be used to perform a computation at the same time. I'll give you some examples to explain these two very basic or fundamental feature of quantum computation. So you will understand these things like how powerful quantum computing could be by just introducing or counting all the possibilities that matters. Quantum computing is actually interdisciplinary, right? It requires knowledge of the maths, physics, and coding. So this is the thing that we need to embrace, that while working in the quantum computing, we should not just restrict ourselves only to the physics or only to the maths. We have to bring the expertise from the maths point of view, from the physics, and also coding or computer science or programming. We have to bring all these fields together to really work on the quantum computers. Quantum computers wouldn't be able to make it reality or happen without this interdisciplinary touch, right? So we have to embrace this, that we have to bring all these major fields all together on one desk. I have no idea about the audience, that how many of you know these figures. So maybe you can type in the chat if you know who is this and who is on the other side. So I'm just seeing some of the comments. Yes, true. Okay, perfect. Atia and Muhammad. Yes, right. So this gives me also idea that how much you know the quantum background, right? So yes, as you rightly mentioned, this is Richard Feynman. He's the one who actually proposed the idea of the quantum computer. He's the one who said that if you want to solve a quantum mechanics, or if you want to do the simulations of the quantum mechanical equations, you need a quantum machine. He just threw the idea, right? And then later on, this guy, Erwin Schrödinger, he's famous for his cat, right? Schrödinger cat. He actually described the principle on which quantum computer would be able to work, and that's called superposition, principle of superposition. So these two names are really our pioneers of the quantum thing, and we are celebrating this year of quantum starting from the Richard Feynman's quantum mechanics. Erwin Schrödinger, he won the Nobel Prize on 1933, and he published a lot of paper, but his first paper it was celebrated universally when he created the revolution. That's, we call it, first revolution in the quantum mechanics. And he proposed this Schrödinger's cat thought experiment in 1935. What was that experiment? We say like God doesn't play dice to the universe. It means that the world we are living is probabilistic, right? it's not deterministic. Like it's probabilistic means everything is possible. There is always a chance of happening anything. And this, then he bring it into quantum mechanics and says, or bring it to a superposition. Maybe I can explain here. I have another slide to show you what is Schrödinger cat box problem, right? Schrödinger cat is very famous. Or maybe I can say something here, but I have another slide. But these are all like interesting things you have seen around on the Schrödinger cat, like 50% chance of happening the things in both ways. I will come back to Schrödinger cat, what he exactly did, how he explained these things in physics and call it as superposition. Okay, it's just for introduction, the start. Now we want to know like how quantum has advantage over classical machines. So let's get an example of a simple maze problem. If you give this simple maze problem to solve to a classical machine, it will take every path at one time. Like, okay, this is the possible solution. This is another possible solution in the second time, the third possible solution, fourth possible solution. So each possible solution at each turn, this machine will give you or provide you. But what the quantum machine will do, quantum machine will take all these possible solutions all at once, simultaneously. So how efficient it would be, right? How fast and how efficient this machine would be. It will be able to take all the possible solutions all at once, simultaneously. And here, just to give you an example, that quantum circuit is actually made up of quantum gates. Yeah, maybe this thing, I should connect it later with the quantum circuits thing. Now, how the machines work, right? What is the computational stack? It is based on a computational stack, rather it is classical machine or a quantum machine, right? It is, it works on a computational stack. So what is computational stack? You see these applications, Zoom, you watch Netflix, MATLAB, Mathematica, whatever programming you are doing, you do the online transactions or these things, these applications you see in those machines and you are using them in daily life. What lies underneath them? This is called a stack, computational stack. So if I go with the fundamental level, it is called bits in classical machines, which has 0 or 1, right? The basic fundamental unit of information is called bit. In classical machine, I call it classical bits. And then you move on to the gates. What gates do, the second step of the stack from beneath, from below, is that you manipulate these bits through gates, right? So the gates, they operate on the bits and you get some new results on your output. So gates are actually manipulating the bits. And then if you combine these gates, you get a circuit. Okay. That's called classical circuit for classical machine and quantum circuit for quantum machine. And then we move to the, we combine these circuits to solve a problem. It's called algorithm, okay? It's different than protocol. Protocols could be like anything, but if you really bringing a solution with that protocol, it becomes algorithm. So you use the word algorithms, and above algorithms are applications which combine these algorithms to play. So this is what you see on this. But do you see any quantum application so far? Not really, right? We don't see any quantum. These are all classical applications, and this lies a classical stack behind it. But we don't see quantum applications in our daily life yet. Why? Because the quantum stack, the quantum computational stack, is under construction. So where we are in 2025, we have qubits. Instead of classical bits, we call it qubits, okay? Quantum bits. We have realized quantum bits, then we have quantum gates, which are mandatory for quantum calculations or quantum computations. We have built quantum circuits, but somewhere here, we are still under construction. We don't see any application because our algorithms are not perfectly working. We don't have some algorithms which are really implemented on what the machines we have built so far. So somewhere here we lie in the quantum world. that's why you don't see any quantum applications so far. Okay. So yeah, this is what we see, and underneath is all, these are transistors, right? So the gates, and then some programming underneath. So you see something here, but you can see what lies beneath these applications is a huge stack. So quantum has potential applications across, I will say, every field of life. Rather you are in finance, cybersecurity, working on the DNAs, genetics, biology, molecular structure, simulations of small molecules, space science, robotics, machine learning, wherever, quantum, you will see the effect of quantum and its impact in each field of life. So I will say, yes, we all have to learn quantum and to implement it in every field of life. Now, let's go back to our stack thing. Just to give you the idea of the major component of this computer or computing machines is called transistor, right? So what are they? Just like in our brains, we have neurons, right? Hundreds of billions of cells around this. Similarly, computers contains billions of miniatures or brain cells. We call them transistors. So actually, gates, I used the word gate before, right? So gates are actually which are manipulating these bits. They are transistors, and they convert inputs into outputs in the form of electrical pulses. So just to give, this is a very basic physics point of view. But now the question arises, do you have any idea, like how many gates do you think in the computer you are using right now? The machines we have in our hand these days, they are really powerful, right? But they are classical machines. Don't forget, even we are using HPC or supercomputers, they all are classical machines. But can you see the efficiency and how, I mean, the error is very low, like they're really good machines. We cannot rely on the quantum machines, what we have so far. So they are really good. But can anyone throw a rough idea that how many gates in these computers we have? How many gates in the computer we have? Any idea? So yes, so millions, yes, millions, but how many millions? It's around 500 million. So 450 is the exact or approximately like number. Yes, so can you imagine, like we have millions of gates, and that makes our classical machine so powerful and efficient, right? And reliable, like we can trust the results coming from there. The error is very, very low. So keep this in mind, that this number, millions, right? Now, when we talk about the quantum machines, we will see like how much we have achieved so far. And then you will see like, is there really a comparison going on between the two? Maybe I'll just give you an idea, like whatever we have now in the area of this quantum, we didn't reach even to thousands. So can you imagine like thousands of gates? Can we compare this with the millions in the classical machines we have? I mean, there is no comparison. So whatever we have in the quantum computer is just beginning of the quantum. It's like a baby computers we have. Like we have to build so much, and once we reach to the millions, suppose even 1 million, it will have a great impact on the computing. But so far there is no comparison. Actually, it's not good to compare quantum computers with the classical one, because classical machines are at their peak, right? They are at their peak. They started with that figure, if you've seen, that's a big room with a lot of cables, and not able to do a lot of that time. I mean, 1940s, it was not able to do that much calculation, which these computers can do now. Like you can have a 4K video. You can see like we are talking from different countries, giving online. You can watch the video, 4K videos. You can make calls, transactions online on these classical machines. But how this technology evolved, this is important to keep in mind. Like a long time ago, I mean, the classical machines were just started with, you have to wait. You remember that time, or if you ask your grandparents or super grandparents, like how much technology they had experienced that time and how it is evolved. So just to raise this point that technology evolves with time, right? And quantum computing is at the beginning of the era of, so it's just building up. Once it's built up, it's saturated, not saturated, but I mean, something in millions we have achieved. I mean, that would be where it will leave an impact in the world. So quantum computing, what are those properties which make it powerful or which we don't see in classical machines? So these are purely 3 quantum properties. First is superposition. Superposition is actually in bits, you have only 2 options, like say 0, 1 or red and blue, but qubit, quantum bit, this is combination of these 2, right? So you have red, you have blue, and then you can build the third state by combining these 2 states, red and blue. And then you can have different shades, right? If you add, like, suppose 10% red and 90% blue, you will get another shade. If you will add 50-50 both, you'll get another shade, right? And if you get 60% red, 40% this, you'll get another shade. So you can create so many shades, like in fact, infinite number, right? By adding these 2 states together. So this is the beauty of the quantum bit. And this quantum bit, or the third state you build, is called a superposition state. Okay, so the fundamental unit for the quantum computer is qubit, while the classical computer is called bit. So bit is limited to only 2 options, 0, 1, on, off, open, close, yes, no. There is nothing third state. But in qubit, you have third state also exist along with these 2. The third property, second property is quantum interference. It's just like you can relate it with the waves, like we have construction or destructive waves, right? 2 waves to each other, and they can cancel each other, out of phase waves. So this phenomena, you can relate it with somehow classical waves also. And the third very important phenomena is called entanglement. Entanglement is like you create these 2 states, and then you can measure if one, you can find the other one, or it will what we should say, like you can entangle, or they are not really correlated. Correlated word is somehow different, but some people, they use it with entanglement, but actually there are 2 different phenomena. So you need to entangle these 2 states. We'll see how we'll get these. I mean, this is where it's not easy to, I mean, quantum entanglement, to explain this, I need 1 hour more to explain quantum entanglement, the phenomena, the physics behind this is beautiful. And to understand this, it's not easy to digest at the first sight. It's how it works. But now people are measuring also. There are many mathematical methods through which you can measure the entanglement. You use this entanglement qubits, you entangle these 2 qubits, and we are using this phenomenon mostly in quantum communication and quantum networking, like Alice-Bob problem, if you have seen. So this is an example where we built this entanglement. Also Bell's states, the quantum states, you've known, if Bell states, they are like maximally entangled states. So you cannot factorize them into 2. Like if the state is written, you cannot factorize it. You don't know like what state is coming from which, like what's the contribution. So these are like really correlated with each other in this way. And if you measure one, it will disturb the second state. Okay, so the first superposition principle, again, it can be explained through the coin, like head and tail system. Like you have a coin, you have head or either tail. But if you rotate that coin, right? If you rotate that coin or spin it for a while, at that time, is it head or tail? So it's actually both, right? It's both head and tail. You cannot tell. So it's both head and tail. So that state is called superposition state. And there are some physical systems where we can keep this superposition state for a long time. That's what we are building qubit by using this principle of superposition to build or to create the third state. Now, coming back to the Schrodinger's cat box problem, if we have seen, I mean, this is really famous, but it's good to talk on Schrodinger's cat in the International Year of Quantum. So he placed a radioactive substance with a Geiger counter and a hammer. Hammer acts as an operator. It will operate on a poisonous gas, and he placed his cat there. And the box is closed. So when the box is closed and inside is this setup, cat with a poisonous gas, with a hammer and some radioactive substance. Now there is a chance that radioactive element will decay and the hammer will hit the poisonous gas. And if the poisonous gas will spread in the box, the cat will become dead. And there is 50% chance of happening that radioactive element will not decay at that certain time t, and the hammer will not act on poisonous bottle or the gas, and the cat will be alive. So before opening the box, the setup is inside. If I ask you, what is the state of the cat? What is the wave function of the cat? We call it superposition, like cat equals to dead plus alive. Okay, so dead plus alive, this plus sign is actually superposition, like it could be both, right? So before opening the box, the wave function is like this. But if I ask you, okay, let's open the box. So if you open the box and you will say, oh, the cat is alive, let's make it alive. So if the cat is alive, you will tell me, oh, the cat is alive because you open the box. Opening the box is actually measurement. Okay, in quantum, we call it quantum measurement. You measure it. And when you perform measurement, you actually collapse the wave function. So the wave function was cat equals to dead plus alive. But as the moment you open the box, you perform measurement. So your wave function will be collapsed into, you will say cat equals to alive, right? You cannot say after opening the box that, oh, I don't know, or cat couldn't be in both, right? Both states. You cannot say after opening the box, oh, cat is dead and alive. No, that's not possible, right? So as the moment you perform measurements, you collapse the wave function and you will say cat equals to dead if you find it dead. If you find it alive, you will say cat equals to alive. So the plus sign is gone, right? So you collapse the wave function in quantum mechanics. This is how we explain. So yeah, there is some philosophy also going around in the quantum that people say, oh, whoever will open the box is actually, if you will find the cat alive, you'll say, oh, he's the creator of the cat. Whoever will make it see dead, he will say he's the murderer of the cat. Some philosophy is also attached with this. Anyhow, the science is there. So this is Schrodinger's cat box. It's a thought experiment, so don't try to do it with your cats. Okay, then coming back to the qubit thing, a qubit, we say a fundamental unit of information on the quantum computer. We have talked about bit and the qubit. What's the difference? You can see bit is 0 and 1 state, but qubit, you build the third state, right? By combining these two states. Now, the question arises that how we will build the qubit, how you will realize the qubit in the physical system. So there are multiple ways, and there is no, what we should say, like a comparison at the moment, that we cannot say that which system, which physical system is the best option to build the qubit, because everything is under construction. So, but these are some very popular, you can say, or very useful physical systems which people are using to build the qubits. Let's talk about, suppose, spins, nuclear spins. People are using nuclear spin to build a qubit because spin can be positive or negative or up or down. Or photonics, people are using photons, the polarization of the photons, like left or right polarizations. So photons or photonics, also a good candidate for building the qubits. Some people are using electronic states, ground and excited states. Some are using, superconductors, Josephson junction, these things, neutral atoms, cold atoms, ion trap. There are many other physical systems which people are using to build qubit. But what is common in all these physical systems is actually two-level system. So any physical system which is two-level system is a good candidate to build the qubit, right? So you can create the third state or combine those two states to build the third state, that superposition state. And if you build the third state, you can protect that state, then actually you are building the qubit. Okay. If someone asks, like, okay, what is the best physical system, we cannot answer at the moment, right? Because it's under construction. There are pros and cons of each physical system. Let's say you have superconducting qubits, like IBM, Google, or these companies are making quantum computers based on superconducting technology, right? Superconducting physical system. But they are working at very low temperature, millikelvins, and you need cryogenic conditions, and so very, very low temperature. So you cannot bring that into your own desk, right? So, but they are fast qubits. But if you compare with the spin-based quantum computing, spin-based quantum computing is working at the room temperature, but some issues like initialization or some, and they are slow as compared to this. But yes, at least you can bring it into your room, into your life, right? Because it works at room temperature. Cold atoms are also getting very famous. So I mean, from all around the world, the people are really trying to build qubits wherever they are working on to see, until we get a quantum computer, so we can debate on this, like, oh, this system works well. Or this, for the time being, all systems, they have their pros and cons to work. So I hope I have conveyed the message that they are building, like Microsoft topological quantum computing also, they are building qubits from this. So yeah, okay, let's go to quantum circuit. What is quantum circuit now? Defining quantum circuit is actually you are just combining quantum gates. So what are quantum gates? Here, if you can see on this a quantum circuit, this is a just conventional way that how we draw this quantum circuit. This is qubit instead of bit. In bit, you just see zeros or ones, right? But if you see this Dirac notation, Ket notation, it becomes qubit. You come into quantum world, so you define it in this Ket notations, so it becomes qubit instead of bit. Okay, and then these lines are qubits. So how many qubits you have in this circuit is 3, and then these are quantum gates. H is for Hadamard gate, and this symbol is for C naught gate or control naught gate or CX gate also it's known. So this X gate is just like as in classical gates also we have this. But these two gates are fundamental quantum gates. In your classical machines, you don't have these two gates, Hadamard gate and C naught gate. Why? Because Hadamard gate is responsible for superposition. This gate provides superposition state. So you don't have this in classical machines. So this is pure quantum gate. And then C naught gate is responsible for entanglement. It entangles these two qubits, right? So this is again a pure quantum gate. So these two gates are called fundamental quantum gates. We don't find them in classical machines or classical circuits. X gate, Y gate, we have tuning gates and many other gates. This is again a C naught gate, but it's doing or performing entanglement on the first with the third qubit, right? It is a control and it is the target qubit, and it operates on this. And this sign shows the measurement, and at the moment you perform measurement, as the moment you open the box of the cat, right, you will know the answer. Either it would be 0 or 1. But at this stage, suppose after Hadamard gates, what would be the state? So the state would be 0 plus 1. Like we call it superposition state. This is actually adding 0 plus 1 by square root 2. I'm not going into much detail, but yeah, this is normalized type form. So you will get a superposition state. And at this stage, you will find entanglement. But as you perform measurement, you will break it and you will get a classical results, either 0 and 1. And then you store it into your classical bits and you'll use it something. Okay, so this just rough idea. And these circuits you can draw, and you can implement these on many quantum programming languages. For example, Qiskit is very famous, coming from IBM Quantum Lab. So we sometimes, our students are using Qiskit language to draw the circuits and implement it on the quantum machines, hardware, and also simulations. Now, let's talk about the current state of quantum computer. Current state of the art is actually under construction, right? So this is a quantum computer, Google quantum computer. You can see how it has a resemblance with our classical computers, very old classical computers, the initial one, right? Why? Because it's taking a lot of space, very big rooms, a lot of cables, a lot of, so it is still in the lab. It didn't come on your desk like the classical machines now you have in your pocket, right? The mobile phones, the laptops, the iPads, you have the machines. You can take it in your pocket and your desk, but quantum computer, you're not having it in your hands or something, right? So it is still in the labs and under construction. So it's not good to compare the quantum computer for a classical computer, which is now at its peak. It is at its maximum level, maximum efficiency we are getting it. If we go either smaller, more smaller, we are actually entering into quantum regime, and then we have to embrace quantum or quantum mechanics to build the computation. And that's how we are transforming our technology from classical to quantum. Okay, so I'll be just finishing up the quantum computing part here by, I hope I have emphasized a lot that quantum is everywhere. And then you will see it's a quantum technology when say it's not about only quantum computers, it's about quantum sensing, quantum communication, quantum optics, condensed matter physics, quantum chemistry, high energy physics, particle physics, everywhere there is quantum. It's not only in quantum computers that we need quantum, right? So quantum, for me, what's currently I'm working on a project based on the quantum sensing. So what is quantum sensing? Quantum sensing, actually, you want to detect the weak signals, which you cannot detect with the classical sensing or sensors, you can say the machines we have, it's the classical level. We cannot sense those weak signals, but through quantum, by applying quantum in the sensing devices, we will be able to detect these weak signals and can apply it for different applications. So I would like to talk about at the end on this quantum sensing project, which I'm working on. So yeah, so what platform or what physical system I'm having to do this quantum sensing is diamond. Diamond is a crystal, right? Hard crystal, you know, but we are using their spin defects. So what is spin defects in diamond? It's called nitrogen vacancy centers or NV centers in diamonds. Okay, so these centers, we can fabricate it. They occur in the nature, but very, very rare. So we can fabricate those diamond chips with these spin defects, which I call it NV centers. And then we are using it for our quantum sensing applications. So this is a real quantum sensor, I mean, NV center chip in diamond. It's 4x4 millimeter in size. So some companies now, it is commercial, like people are building these or fabricating these chips and selling. So it's commercially available, and then you can do the quantum sensing through NV in diamond. This is a very exciting and emerging field in quantum sensing. People are also building quantum computers based on NV in diamonds also. But in our lab, we are more on the quantum sensing side using this. So the key message for quantum sensing or this topic is that, as I mentioned, nitrogen vacancy, or we call it NV center, it's a solid state spin defect in the diamond, okay? And atomic size quantum sensor for what? It is sensoring electric field, magnetic field, strain, and temperature around it. So, but we are more focused on the magnetic field. So it's called magnetometry. And we believe it's a promising tool to perform magnetic resonance on a very small length scale, like microscale and nanoscale level now also. So yeah. And also we are looking for some novel techniques. I mean, this novel technique is really looking for novel applications. And in our minds, we have some ideas how to sense asphaltene salt in the petrochemicals or in the petroleum industry, if we can use our sensors, because, you know, we are in UAE, petrochemical industry is a huge economy, lies on this. So this could be a great potential. Now let's talk about, on the NV centers in the diamond. You see this is diamond structure, all carbons around, right? But how we create a spin defect. So actually we bombard with the nitrogen gas, right? So nitrogen takes one carbon away, like one carbon atom kicked off, and nitrogen takes its place, and then one carbon is vacant, and there is it's created a vacancy, and we call it nitrogen vacancy center, NV center. Nitrogen vacancy, like two carbon atoms actually kicked out of the carbon crystal. So one nitrogen atom will take the place, and the second you create the deficiency, and this makes its spin effect, right, inside the diamond. Otherwise, without spin, the diamond has no spin. So here you created that spin in the diamond, and this itself, NV center, is an atomic sensor in the crystal. There are, as I mentioned, there are many companies who are fabricating these NV centers in the diamond. The simple, like, these are the steps usually they do, like nitrogen implantation. You dope during the growth, then how shallow, how deep, how dense, it depends on your implantation method of the nitrogen. So you can create different density of NVs in the crystal, and it matters, okay, in your experiments. Then you do annealing, ionizing it, and then surface termination, and your NV center in the diamond is prepared. For us, in the lab, we are not fabricating the chips. We are getting the chips, and we are using for our setup, okay? So what is the key principle of NV diamonds? I'll talk about this with this energy level diagram. I think that would be good. If you shine a green laser or green light on the diamond crystal with NV center, it will emit a red light. So all this phenomena, we calculate then this red light fluorescence, which is spin-based, okay? So the ground state of NVs is triplet ground state, 0 and plus minus 1, degenerate without magnetic field, and by adding magnetic field, it will create energy gap, right? So you shine green laser light, green light, and then it goes to excited state, and if it comes back, it emits a red light. So this as one step. The second step, if you see that the electrons or the spins coming from plus minus 1 state, they goes to excited, right, plus minus 1 state, they adopt an additional pathway. Instead of just coming back to the ground state, they adopt an additional pathway that's through intersystem crossing, that call it this intersystem crossing, that there is a metastable state, and which is little slower, and then it goes back to 0 state. So actually at thermal equilibrium, they are having Boltzmann distribution according, right? They are equal spins in both sides. But when you shine green laser, it will go from 0 to excited state and comes back, giving you red light. Plus minus 1 will go to excited, plus minus 1 comes back, but not really. What they are doing, they are going here, additional pathway, and then they come back. Instead of here, instead of going to plus or minus 1 state, they go back. They prefer to go back to the 0th state. So what you are actually creating here is spin polarization. Before this, all the spins were equal, and then you create this spin population in 0 state. And when the light emitted from this 0th state, you can calculate it, optically read out how you will manipulate it with microwave. Then we shine microwave. Microwave, what they will do, it will start oscillation between 0 to minus 1 and coming back to the cyclic movement, right? It's called Rabi oscillation. And then you read out, optically you read out. So the fluorescence you are getting, we use a detector, APD, avalanche photo detector, to translate this optical signal to our then voltage, and then we can see that this is coming from 0th or plus minus 1 state, right? So microwave frequency, if you see this dip in the fluorescence, so actually we are counting number of photons, fluorescence or photoluminescence effects, right? So it's actually you're counting number of photons. In the start, it is supposed maximum, right? But once you see this dip lying in the gigahertz, because this distance energy level is in gigahertz, around this 2.89 something, you will see a dark spot. Dark spot mean like all all the spins have moved to this state, right? So you see a dark spot. But if the spin or the light is coming from the 0 state, you see the bright light. So here is the bright light coming. You see the darkness, photoluminescence falls to almost 0 or very dark, and then it comes back. But here, why you see 2? Because you have applied magnetic field. Here's 0 magnetic field, there 3.6, and then you can increase magnetic field, and the magnetic field you are increasing, you can calculate the difference between the two, right? And then this will give you the idea. You can calculate the magnetic field actually. Nearby magnetic field. So this is how we sense the magnetic field, actually by measuring the distance between the two dark tips. So yeah. Now actually, as I mentioned, that NV diamonds, they are useful for different applications. For us, we are focused on magnetometry. Magnetometry means you are sensing magnetic field. We are not sensing electric field, stress, or temperature. We are focused on sensing magnetic field. So it's called magnetometry, NV magnetometry. So you see, we have, suppose, NV diamond, and you bring a magnetic field closer to it, right? And this is a microwave pulse sequence, like we applied microwave, you shine green laser. So what you see as the magnetic field come closer, you see the fluorescence effect, it changes, right? It differs. So this fluorescence effect, the lights we read out, we translate it, will give us the strength of the magnetic field nearby. So this is how magnetometry works with NVs. So quantum sensing, the basic of this, as I mentioned, like any quantum system which is 2 state is a good candidate. So this our spin system of NVs. It is either in 0 or plus minus 1 state. So 2 states, right? So we can build the 3rd state, a superposition state. So in the quantum world, how we locate or no, how we represent our states is called block sphere. So this is a block sphere. Like you locate your points, right, in Cartesian region, like x, y axis, and it can define like where the point is. So in quantum states, we represent in block sphere. So if it is up, we call it 0. If it is down, we call it 1 or minus 1 in this case, suppose. And then if it is in the middle of up and down, it is called superposition state, or any state actually, any point other than up and down, any point in this is a superposition state. But along x-axis, suppose this is the middle of plus z-axis or minus z-axis, is 50-50, right? Have a chance of being in 0 or 1 state. So it's like a maximally, you should say, maximally superposition state, you can say, right? 50-50% chance. Other than this, if some point lies here on the block sphere, so it has more chance of being in the 0 state when you measure it than this, right? Or any state which is somewhere here or near to, you can say, down on this minus the axis thing, it will have more chance of being in the 1 state. So just to give you an idea that any point on this block sphere is a superposition state, and you can create this by doing this, what we did, that you bring it back. If the light excited state, when it falls down to 0 state, it will give you a bright light, right? Fluorescence, you calculate is bright. But if it's coming from plus or minus 1 state, the light would be dim, right? So, and this oscillation you are building from 0 to plus minus state, these also, they are moving, right? Through microwave, we applied microwave. So microwaves actually manipulating this thing, right? And here we are building the qubit. Qubit means like at this time, they are moving like this here, right? 50-50 chance, and then maybe they reach here and then come back. So this oscillation or this state, we call it coherent state or superposition state. In quantum sensing, we let this coherent state to interact with the environment. This is how the quantum sensing principle works. But in quantum computing or quantum simulation or quantum computing community, they protect this coherent state. But in quantum sensing, we let this state to evolve and to interact with the environment. So maybe this, this is, so you have initialized your quantum state, right? And then you let it to interact with the environment. and then you're Hamiltonian, like it involves the state, and then you read out in time, or you can repeat this cycle. So this is the basic principle of quantum sensing, and this is how it is where it is different than quantum computing. In quantum computing, you protect this coherent state, what you create, you preserve it. But in quantum sensing, you let the state to interact. So it is more practical, and I think it is more, rather in quantum computing, it's really getting hard to preserve this quantum state for a long time and things like this. So yeah, I think I've seen it's a lot about this. Then this is the experimental scheme for our experiment, which we are building in our lab to build this quantum sensing based on these NV centers in the diamond. As I mentioned, it's almost, we have startup, but I've been bringing some results. It's still, we will say, it's kind of under construction, but this, how it looks like, it has some optical parts and some electronics involved. You have to give this optical part for the green laser, you shine it, you have to bring it into, in the diamonds, right? And then there is a photodiode and APD, and then it's connected with the data acquisition unit to calculate. So this all optics you see to bring the green laser on the diamond chip, and then some electronics involved to read out this thing. For this, we also, just to say, on the quantum desktop we have in our lab, it is 2 qubits quantum computer based on a spin technology, and based on, you can say, nuclear spin technology. So nuclear spins are manipulated as 2 qubits here in our system, and we use this for education purpose. So yeah, just to add on, and this is some outreach we are involved from our center to spread the awareness on quantum information, quantum computation, in general, quantum technology. These some activities from the last year. And yes, I think I'm fine with the time. So thank you very much, and please, I'm open for any questions.
Thank you, Dr. Amaria. Thank you for this interesting talk. Anyone have any question?
Yes, Dr. Muhammad. Can I ask?
Yes, go ahead.
Yes, thank you, Dr. Amira. And I want just to ask here.
Dr. Amaria. Dr. Amaria.
Amaria, yes. I am sorry. Yes, just I want here to ask about to how to implement the qubit, or the superposition of the qubits. I want to ask here if we have, for example, a way to implement the phase of the wave. I just want to explain here that I have some research that can control the phase of the wave when it incident on the some thin films. So is this an implementation for quantum qubits or quantum feature in general, or I don't understand the implementation very well?
Yeah, thank you for the question. I would say I'm not really can't say anything with the surety or with my expertise. I think yes, I think the phase people are manipulating the phase factor in the qubits. So maybe you have good understanding. I mean, you are right in understanding this, the phase factor bringing and realizing it into the qubits.
So you encourage me to for example, to publish some paper, or to start to implement, for example, maybe simulate this before implement it in hardware.
Yes.
Because I already have a result from MATLAB, because I already have simulated the incidence of electromagnetic wave on thin films, and then by some way I can manage the the phase angle to change it depending on some voltages.
Yeah, I think that could be interesting. If you could perform some simulations, and not only to create superposition, then we have to see how long that current state you can preserve it to, to give a good justification of your calculation.
Yes, in fact, before I talk about this, when I simulate the result of incidence of electromagnetic wave on thin films, some I already published 2 papers for lossless and lossy materials, but I hide some results because I think this results may be more useful to be published as a quantum features or a quantum result for this simulation. So I think I thinking now to how to maybe to reform the results or to show the result in the from the point of view from quantum physics or quantum information theory, so I can maybe yes, but maybe this need yes to contribute with someone who can ensure that if this result is can be implemented as a quantum information or quantum qubits. Yes.
Yeah, I see your point. Yes, I think we have to look into details of this.
If you don't mind, you can share with me or with us your email, and after that maybe I can show you how the result is, and you can yes to contribute with each other and how to yes to
Yes, sure. I'm open for any kind of collaboration. It would be my pleasure. And you can see the email address on the screen, right? It's my last slides. It's here, my email address. So please, you're very welcome to reach out to me through this email, and maybe we can have a look into details of this. So yeah, it would be interesting.
Thank you.
Yeah.
Thank you, Dr. Muhammad. Thank you, Dr. Amaria. There is another question by Dr. Mohab. Go ahead, Dr. Mohab.
Thank you, Dr. Amaria, for your talk. It was very interesting. I have 2 quick questions, please. The first one, can we use this technology in detecting the gravitational waves? The second question is, can we get back, please, to the slide that shows the cycles, the 3 cycles of making the process, then measuring and getting back to read yes, the initialization. My question here is, after initialization, the interaction has been made by the environment, then there is a change in the state, and then we should get to measuring this change. I get confused here. Does the measuring process affect the state after the first interaction happens with the environment, and then how can we get the results without confusing the measuring process that has been made? Thank you.
Yeah, thank you very much for your questions. It's a very important point you raised. So yes, we have initialized our quantum state, right? Superposition state. And then you see when it interact with the environment, actually it's bringing the phase, as my first question was also we were discussing. So here is the phase accumulation, we call it, right, with the environment. So you will see it's not changing here. It's actually it's in the same on the Bloch sphere, but it has accumulated a phase. So if you see here, this is the state. But what is the difference between here to here, or from psi naught to psi? You have added the phase, actually, right? So you accumulate the phase while letting the environment to interact. Letting the state to interact with the environment. And then when you read out, this is the beauty of this system, that we are reading it optically, right, through light. So we have bright or dim states, right? So you have bright and dim states. And then when you read out, you are reading the optical signal. That optical signal means that you are reading the fluorescence. You are reading the number of photons coming out from the NVs or from the diamond. And that number will give you, because it is spin dependent. So if it's coming from if it's dim, right? Suppose if it's your readout, your fluorescence is dim. Suppose you're not getting a bright signal. It means that the state is in zero state. Okay, and then if it's coming from other, so the optical signal or your fluorescence, your readout is spin dependent. This is very, very important of NV system, or this whole idea of using these NVs for quantum sensing, that your optical signal or your readout is spin dependent. So it is very easy for you to say that this signal is coming from either from zero state or from plus state or from minus state. So this is how you will distinguish after reading the signal. You can distinguish like it is coming from which state. So I think did I answer this question? Or
I got it. Yes, thank you. But the first question was, can we use
gravitation?
Gravitational wave detection?
Yeah, this is a hard question for me. Like, it is, as I mentioned, it's an emerging field. The goal is somewhere, but for the time being, I don't really see it's happening very near. As I said, it's NV centers or the quantum sensing using this diamond is not very old. It's emerging fields, and it's improving day by day. Like, we have good magnetometry, or we are using this for MRI machines also in the sensing, or NMR based many applications of this technology. But I think for gravitation, it's still a question.
Yes. Thank you so much, Dr. Amaria.
Thank you.
Thank you, Dr. Mahab. Thank you, Dr. Amaria. Any more question?
Yes, Dr. Muhammad, please.
Go ahead.
Regarding this slide shown now, I see here in the readout stage, the amplitude changed from 1/2 to A square or B square. Does this mean that the phase can change the spin here, so the spin affects the amplitude, or what? Can you explain, please, these amplitudes?
Okay. Yeah, thank you for your question. Again, sorry, maybe here. Let me just fix it here. Yes. So actually, this is what the measurement is. When you read out, actually, what you are reading, you are right. You are reading the probabilities, right? The mod squares of these numbers. A mod square is actually A or B is, this is the initial you have, this is A or B, but when you read out, you don't read A, right? Or B, you do the probability, you calculate probability, read out. So that's how we are doing readout. It's just a schematic, like representation. I call it A mod square or B mod square. Okay, but here during the interaction, what we introduce is the phase.
Let me explain her question. In initialization step, you prepare your system as a uniform superposition. So all probability amplitude is 1/√2. Then in the interaction, you as a result of the interaction, you cube it with the environment. There is a phase is gained here. Asma asks, in the readout step, the figure explains that you measure modulus A square and modulus B square. Is A square here 1/2 or different?
Oh yeah, no, it's with different. That's why I just generalize it with A mod square.
What is the reason of this distortion in the state? This is her question.
Yes.
Oh, okay. Yeah. So you see, this we call it A, and this is B. what happens here is actually we accumulated phase accumulation, and then we apply another pulse, which I didn't add it here, but maybe somewhere here, that we bring it back to the axis where we can do the measurement. So there is some change that would bring this change in the amplitude. So I cannot say exactly that this would be 1/2 mod square. Otherwise, I could write this. So that's why I just said A mod square. Like there would be changes happening during this measurement. So it will change to A mod square.
Okay,
Thank you, Dr. Amaria. Thank you, Dr. Amaria. Any more questions?
Yes, Doctor, please. Can Dr. Amaria explain briefly how nitrogen vacancy center creates a spin defect in diamond?
Okay. Okay, maybe not here. Okay, I think, yeah, maybe this good thing. So the diamond itself is spin free, right? It's all carbons here. But when we implant nitrogen, somewhere here you can see, yeah. So when we implant nitrogen, nitrogen is now pentavalent, right? So some electrons here, and then you create a vacancy also. So actually you have lone pair and free electron there, which is not paired. So that will create the spin inside the structure. So we call it like, that's why you have seen this spin in this picture, not here, because this is spin free, right? Carbon, all tetravalent, they are. This is more into like chemistry, right? The people who are implantation nitrogen or through chemistry, we can maybe go into more details. But I think this would be enough to understand that you are bringing a spin from an unpaired electron there in the crystal by adding nitrogen. Nitrogen is pentavalent, right? So it has a free electron, and then you have a vacancy. So combining this electron ratio in the crystal, it creates the spin. And then that spin is like a triplet ground state and so on, which I explained in energy level diagram.
Okay, thank you. I have another question, please. In the slide which you show 3 levels of energy and another 3 levels, can you show us the slide, please? Yes, this one. I don't understand what is A to the superscript C. Is this and E to the superscript E?
You mean this?
And this metastable. Yes. What these labels represent?
Okay. So this A3 is this in our community in NV diamonds, we use this for ground state, A for ground state, and E for excited state. And this 3, you see, this is triplet state. So three states, 0, +1, -1, 3 states. That's why it's called triplet ground state. And this is called, this is called triplet excited state. And this is metastable state. So it is in between A and E, right? It can, but why you see 1? Because it is singlet state, only 1 energy level.
Okay, thank you. Thank you for this new information for me, really. So ground state here is triplet levels, 3 levels, and all these represent ground state, right? And the upper 3 is okay.
Excited state, this is ground state, and this is metastable state, and singlet state, this is singlet state.
And A/E means it is in between, right?
In between, yes. Metastable or intermediate state, you can say, like in between ground and excited state, there is an energy level.
Okay. Thank you very much. Thank you.
Thank you. Any more questions? Thank you, Dr. Amaria, for this interesting lecture. Thank you. It was very, very amazing lecture. Thank you. Nice to meet you.
My pleasure. Thank you for having me.
Thank you. You are welcome, and we are looking to see more, to listen to more talks for you. Thank you very much.
Yeah, sure. Okay. Thank you, everyone.
Thank you.
Thank you so much. Thank you, Doctor.
Thank you, Doctor.
Assalamu alaikum.
Thank you, Dr. Maxim.
So.
السلام عليكم.